Imagine holding your smartphone in your hand, a device so small it fits comfortably in your pocket, so light that you barely notice it when you carry it. And yet, hidden inside that device is one of the most extraordinary inventions in human history. Something so small that you cannot see its most important components with your naked eyes. Something built from structures measured not in millimeters, not in micrometers, but in nanometers, billionths of a meter. A technology so tiny that some of its parts are only a few dozen atoms wide. And yet, this tiny object powers your entire digital life. Your social media, your videos, your games, your navigation, your photos, your artificial intelligence assistants, and almost every piece of modern technology you use every day. This remarkable invention is the computer chip, the heart of the digital world, the invisible engine behind modern civilization. And today, humanity is engaged in one of the most fascinating technological races in history. A race to build the smallest computer chips ever created. Chips so incredibly tiny that engineers are approaching the very limits of physics itself. A race that is shaping the future of artificial intelligence. Smartphones, supercomputers, autonomous vehicles, space exploration, military systems, and perhaps the future of humanity itself. But how did we get here? Why are companies spending billions of dollars just to make chips a few nanometers smaller? How small are the world's most advanced chips today? And what happens when technology reaches the atomic scale? To answer these questions, we must go back to the beginning. Back to a time when computers looked nothing like the devices we know today. The earliest computers were enormous. Not desktop computers, not laptops, not even machines that could fit inside a house. Some of the first electronic computers filled entire rooms. One famous example was ENIAC, a machine weighing more than 27 tons. A machine that consumed enormous amounts of electricity. A machine filled with thousands of vacuum tubes. At the time, it was considered a technological miracle. Yet the processing power of a modern smartphone vastly exceeds what ENIAC could achieve. The problem with early computers was obvious. They were too large, too expensive, too fragile, and too impractical for widespread use. If computing was going to become part of everyday life, computers had to become much smaller. Everything changed in 1947. That was the year researchers at Bell Labs invented the transistor. The transistor replaced bulky vacuum tubes. It was smaller, faster, more reliable, and far more energy efficient. This invention became one of the most important breakthroughs in human history because it made miniaturization possible. For the first time, engineers could imagine building powerful computers without filling entire buildings. But the story did not end there. Soon, engineers had an even bigger idea. What if multiple transistors could be placed on a single piece of silicon? Not just a few, but hundreds, thousands, millions, and eventually billions. This idea led to the invention of the integrated circuit. And from that moment forward, the race towards smaller chips truly began. In 1965, an engineer named Gordon Moore made a prediction that would become famous. He observed that the number of transistors on a chip seemed to double regularly over time. This observation became known as Moore's Law. For decades, the prediction remained remarkably accurate. Every new generation of chips became smaller, faster, more powerful, and more affordable. Year after year, decade after decade. What once required a room-sized machine eventually fit onto a desk, then into a briefcase, then into a pocket, and today, into devices smaller than the palm of your hand. To understand how extraordinary modern chips are, We need to understand a very important unit of measurement, the nanometer. A nanometer is 1/1000th of a meter. To put that into perspective, a human hair is roughly 80,000 to 100,000 nanometers wide. Modern advanced chips are manufactured using processes as small as 3 nanometers. That means their critical structures are thousands of times smaller than a human hair. The scale is almost impossible to imagine. At these dimensions, even ordinary microscopes struggle to reveal the details. Today, some of the most advanced chips in the world are produced using 3 nanometer technology. Companies like TSMC and Samsung Electronics are leading this race. Their manufacturing processes allow billions of transistors to fit inside a single chip. And every time engineers reduce transistor size, several important benefits emerge. First, more transistors can fit into the same area. Imagine a city. If houses become smaller, more houses can fit on the same piece of land. The same principle applies to transistors. Smaller transistors mean greater computing power. Second, smaller transistors often consume less energy. This improves battery life, reduces heat generation, and lowers operating costs. Third, shorter distances allow electrical signals to travel more efficiently. This can increase performance and speed. But making chips smaller is far from easy. In fact, it is one of the most difficult engineering challenges humanity has ever attempted. Because when transistors become extremely small, physics begins to behave differently. At everyday scales, electricity follows predictable rules. But at the nanometer scale, quantum effects begin to appear. One of the biggest challenges is something called quantum tunneling. Normally, electrical barriers are designed to control the movement of electrons. But when structures become too thin, electrons can sometimes pass through barriers they should not be able to cross. Imagine building a wall designed to stop people from passing through. But if the wall becomes unbelievably thin, people somehow start walking through it. That sounds impossible. Yet something similar happens at the quantum level, and this creates major problems for chip designers. As a result, every new generation of semiconductor technology requires entirely new innovations. New materials, new transistor designs, new manufacturing techniques, and some of the most sophisticated machines ever built. One of the most extraordinary machines in the world today is used to manufacture advanced chips. These machines use a process called extreme ultraviolet lithography, or EUV. The technology is produced by ASML. Each EUV machine can cost hundreds of millions of dollars. They weigh hundreds of tons, contain hundreds of thousands of precision-engineered components, and represent one of the most complex manufacturing systems ever created. Using extremely short wavelengths of light, these machines essentially draw transistor patterns onto silicon wafers. Without EUV technology, many modern chips simply could not exist. This complexity is one reason why advanced semiconductor manufacturing has become strategically important. Building a state-of-the-art semiconductor fabrication facility can cost tens of billions of dollars. Only a handful of companies on Earth possess the technology required to manufacture the most advanced chips. As a result, computer chips are no longer just a technological issue. They have become an economic issue, a national security issue, and even a geopolitical issue. Countries around the world are investing heavily in semiconductor development because they understand a critical reality. The future of technology depends on chips. Artificial intelligence depends on chips. Advanced military systems depend on chips. Modern communications depend on chips. And global economic competitiveness increasingly depends on chips. But the race is far from over. Researchers are already developing 2 nanometer technologies. Some are exploring 1 nanometer concepts. Others are investigating entirely new approaches to computing. Because eventually, there may be a limit to how much smaller traditional transistors can become. After all, atoms themselves have physical dimensions. At some point, there may simply be no room left to shrink further. When that moment arrives, innovation may shift in a different direction. Instead of making transistors smaller, engineers may build chips upward through three-dimensional architectures. They may create neuromorphic processors inspired by the human brain, or develop powerful quantum computers that operate using entirely different principles. The future of computing may not be defined solely by size, but by entirely new ways of processing information. Yet, regardless of what comes next, one fact remains extraordinary. Every time you unlock your phone, watch a video, send a message, navigate a city, use artificial intelligence, or connect to the internet, you are benefiting from decades of relentless miniaturization. A journey that transformed computers from room-sized machines into billions of transistors packed onto a piece of silicon smaller than your fingernail. And perhaps that is the most remarkable part of the story. One of the most important technologies in human history is also one of the smallest. So small that it is nearly invisible, yet powerful enough to shape the modern world. And the quest to make it even smaller continues. Because in the world of technology, the future is often determined not by what is biggest, but by what is smallest.